Today, we're going to dig into a data structure that's so common we almost never stop to ask why it's so good. The array. We're about to find out how this super simple tool is actually one of the most powerful things in programming. And the answer? Well, it has a lot more to do with the physical hardware than you might think. I mean, think about it. If you've ever written code, the array was probably the first real data structure you ever touched. It's that hello world of storing data. You've got a list of things, you stick them in an array. It feels simple, kind of boring even. But that's the big question, isn't it? If they're so basic, why are they the backbone of so many high-performance systems? The secret isn't some fancy algorithm. No, it's hidden deep down in the physical layout of your computer's memory. So here's how we're going to break it all down. First, we'll look at the simple illusion of an array. Then we'll uncover the real secret sauce, the power of contiguity. We'll see why CPUs are basically built to love them, understand their weak spots, and finally figure out how we can use all this to write way better code. All right, let's kick things off by peeling back that first layer. We're starting with what we all think an array is, but you're about to see there's a lot more going on underneath. So from a bird's eye view, an array is just a collection, right? It holds a bunch of things, they're all the same type, and you can grab any of them just by knowing their position, their index. You want the sixth thing? Just ask for index 5. Simple. But that simplicity is hiding something really, really powerful. And now we get to that hidden power, the core concept. There is one single property that explains all of an array's speed. It's an idea called contiguity. So, what in the world is contiguous memory? Well, it's pretty much exactly what it sounds like. When you make an array, the computer finds a single, unbroken, sequential chunk of memory and puts every single element right next to its neighbor. There are no gaps, no detours, just a solid, predictable line of data. And here's where the magic happens. Because of that perfect layout, finding an element isn't a search party, it's just a tiny bit of math. The computer takes the starting point of the array, adds the index you want times the size of each element, and boom, it knows exactly where to go. It's not a search, it's a calculation. And this is the game changer. For an array, getting the 1,000th element is just as fast as getting the very first one. We call that constant time access. Other data structures might have to walk through a long chain of items to find what they're looking for, getting slower and slower as they get bigger. Arrays? Nope. Same speed, every time. Okay, but it gets even better. This isn't just some clever software trick. The actual hardware, the CPU in your machine, is specifically built to take advantage of this layout. It's a perfect partnership between our code and the silicon it runs on. You see, modern CPUs are obsessed with speed, and to be fast, they have to be great at guessing what you're gonna need next. This is built on an idea called spatial locality. Basically, if you access a piece of memory, you're probably gonna need its neighbors pretty soon. So CPUs don't just grab one piece of data at a time, they grab entire chunks called cache lines. Let me walk you through it. Say your code asks for the item at index 50. The CPU doesn't just get that one item. It says, hey, they're probably going to want the next few too, and it grabs a whole neighborhood of data, maybe from index 48 all the way to 63, and pulls it into its own super-fast local memory, the cache. So when your code inevitably asks for index 51, guess what? It's already there. The access is practically instant. And here's the big takeaway. Arrays aren't fast just because they're a smart idea. They're fast because their layout in memory perfectly matches the way hardware is designed to work. They're literally speaking the CPU's language. But, and there's always a but, all this incredible speed comes at a cost. The very thing that makes arrays so fast, that rigid, predictable structure, is also their biggest weakness. Let's talk about what happens when things need to change. So when does all this amazing performance just fall apart? It happens the moment you need to do things like insert an element somewhere in the middle or delete one, or when you simply run out of space. Just imagine this. You need to add a new item at index 2. You can't just drop it in. To keep that perfect, contiguous block, you have to physically shuffle every single element after it one spot to the right, one by one. If you have a huge array, that is a painfully slow and expensive operation. And this brings us to one of the most fundamental truths in software engineering. Arrays make a very clear trade-off. You give up flexibility, the ease of changing things, in exchange for raw, predictable access speed. Now, you might be thinking, wait a minute, I use lists in Python or array lists in Java all the time, and they seem flexible. And you're right. Modern languages give us this awesome compromise called a dynamic array. It handles all the resizing for you automatically. But under the hood, when it runs out of space, it has to create a whole new, bigger array and copy every single element over. That cost is hidden from you, but it is never, ever zero. Okay, so we've gone deep into the why. Now let's talk about the so what. How does all this knowledge actually help us design better, faster systems? It's time to put this into practice. Here it is, your practical cheat sheet. You want to reach for an array when you're doing a ton of random access by index, when you're looping through everything, when the amount of data is pretty stable, and when performance is just non-negotiable. But if your data is constantly changing with lots of insertions and deletions, or if the size is totally unpredictable, an array is probably going to be a bottleneck. And that brings us back to the most important idea of this whole explainer. Arrays are amazing, not because they're simple, but because they deeply respect the physical reality of how a computer actually works. It's the perfect marriage between software design and hardware architecture. And that's what I want to leave you with. Building truly fast systems isn't always about a more clever algorithm. So often, it's about understanding your data's memory layout. It's about knowing where your data actually lives. The next time you reach for an array, remember, you're not just using a simple data structure, you're speaking the language of the hardware itself.